Greetings, distinguished chairperson, conference organizers, fellow researchers, academics, and delegates. And thank you for giving us this opportunity to present our research. My name is Maria Venthan Thuraisingham from Durban University of Technology, South Africa. And this work was conducted together with my co-author, Professor Mogivani Rajkumar. Yeah. So today I'm presenting our research titled A Multi-Layered AI-Based Cybersecurity Framework for Real-Time Threat Detection in IoT System. In simple terms, we can say that our research looks at how artificial intelligence can help IoT systems detect and respond to cyber threats in real life. So with that introduction, let me briefly explain the motivation of this study, of this research. So IoT devices are now everywhere in smart cities, healthcare, industries, agriculture, transport, and even our homes. But the number of connected devices increases. The attack surface also increases. So there are three main challenges. First, more connected devices create more possible entry point for attackers. The second, many IoT devices have limited processing power and memory, making advanced security difficult to implement directly on the devices. The third, cyber threats such as distributed denial of service, malware, unauthorized access, and zero-day attacks are consistently changing. For example, if a smart sensor suddenly starts generating thousands of unusual network requests, the traditional secure may not recognize that attack immediately. AI, however, can identify that the behavior itself is abnormal. Therefore, we need security that is proactive, scalable, and continuously learning. The main research gap we identified is fragmentation. The existing solutions such as encryption, authentication, and intrusion detections are important, but they often operate separately. Our study, therefore, proposes a unified multi-layered architecture. There are three main contributions. First, we propose a multi-layered IoT cybersecurity architecture. The second, we integrate machine learning for real-time anomaly detection and adaptive response. Third, we provide simulation-based validation. So instead of using AI only to detect an attack, our framework connects detection, decision-making, and response and continuous learning. Our framework is supported by three theoretical perspectives. The first is machine learning theory, which enables the system to learn patterns and classify normal and malicious behavior. The second is behavioral biometrics, which helps us identify unusual behavior. For example, if a device normally communicates 10 times per hour, then suddenly communicates thousands of times. This behavioral change may indicate a threat, right? So the third is trust management, which helps evaluate whether devices and interactions within the IoT environment can still be trusted. So in a simple terms, machine learning helps us learn. Behavioral analysis helps us observe, and trust management helps us assess reliability. Our methodology combines conceptual framework design with experimental simulation. We followed five main stages. The first, we identify key IoT security problems. Second, we design the proposal multi-layered framework. Third, we considered three machine learning techniques. Fourth, we used the benchmark data set, that is UNSW NB15 and IoT 23 for simulation. And finally, we evaluated the models using accuracy, precision, recall, and F1 score. So the process moves from problem identification to framework design, model development, simulation, and finally, evaluation. Right. So this is the main contribution of our research. Let me explain the framework from left to right. The first is the data collection layer, where we collect sensor data, network traffic, and user interface. Second is the data processing layer, where the collected data are cleaned, normalized, and prepared for analysis. The third is AI analysis layer. Here, machine learning techniques classify behavior and detect abnormalities. Fourth is the decision-making layer, where the system determines the severity of the detected threats and decides what action should be taken. Fifth is a response layer. The system can generate an alert, restrict access, and then isolate the compromised devices or block malicious traffic. Finally, we have the feedback and continuous learning layer. This allows the system to learn from previous incident and improve future detection. For example, imagine a smart factory sensor suddenly producing abnormal network traffic. So our framework collects that traffic, analyzes it using AI, identifies the anomaly, make a decision, then isolate the device if necessary, and then learn from that incident. So in simple terms, the framework follows data, intelligence, decision, mitigation, and the last one is learning. To evaluate the framework, we considered three machine learning models. Those are random forest, then SVM, and K means clustering. We used two benchmark cybersecurity data sets, that is IoT 23 and UNSW NB15. These contains both normal and malicious network traffic. We then evaluated performance using four standard metrics. Those are accuracy, precision, recall, and F1 score. So the objective was to determine how effectively these machine learning approaches could support threat detection within our proposed framework. Now, let us look at the main result. You can see from the graph, random forest produced the strongest overall performance. It achieved 96.7% accuracy, 95.9% precision, and 96.2% recall, and 96% F1 score. But SVM achieved 92.3% accuracy, while K-means achieved 88.4%. Therefore, random forest outperformed the other two approaches across the reported metrics. However, our main point is not that the random forest will always be the best algorithm. Rather, these results demonstrate the potential effectiveness of machine learning-based threat detection within our proposed framework. So, what do these results actually mean? So, there are three important findings. First, improved detection. That means AI can identify abnormal behavior beyond traditional rule-based detection. The second one, adaptive security. The framework connects detection to detection making and response, while the feedback mechanism supports continuous improvement. The third one is scalability. The layered architecture separates data collection, analysis, decision making, and response. So making it suitable for heterogeneous IoT environments. Therefore, the key message is AI should not be used only as an isolated classifier. Its real value comes when it becomes part of an end-to-end cybersecurity process. There are also some limitations. First, our evaluation uses benchmark data set and simulation rather than real world IoT development. The second one, AI models may require computational resources that small IoT devices do not have. And the third one, machine learning performance depends strongly on the quality of the available data. So therefore, the future work will focus on real-world IoT implementation, real-time data streams, and the development of lightweight AI models for resource-constrained devices. To conclude, I would like to remember 4 words: detect, decide, respond, learn. The machine learning helps us detect abnormal behavior. And then the framework then decide how serious the threat is. It responds by taking an appropriate security action. And finally, the feedback mechanism allows the system to learn. So our simulation showed promising results, particularly with random forest, which achieved 96.7% accuracy. But the main contribution is the complete architecture that connects AI-based detection with the decision-making, response, and continuous learning. Ultimately, our goal is to move IoT cybersecurity from being simply reactive towards being proactive, adaptive, and scalable and intelligent. So, yeah, ladies and gentlemen, thank you very much for your time and attention. I would also like to thank the conference organizers once again for this opportunity. Yeah, thank you. And I'm happy to take any questions.